Um, Good evening again, ladies and gentlemen. Welcome to CIE seminar today. Today we have the honor to have Dr. William Kao to talk about photonics. Before that, I will just need a few minutes to introduce our organization and also introduce him. Hi, William, can you hear me okay?
Yes.
Okay. So if you have not seen any our media channel, please subscribe. We have a newsletter that is every 2 weeks. We have Facebook, Line, WeChat, LinkedIn, YouTube, and I will talk a little bit more about the YouTube channel because that's where we keep all our recordings from past events. Our organization, Chinese Institute of Engineers, was established in Cornell University in 1917 by several famous study abroad students from China, Zhang Tianyou and Lin Hongxun. And the CIE just celebrated its 100th anniversary in Bay Area in 2017, 5 years ago. And for this year, it is our 105th anniversary. Our San Francisco Bay Area chapter was established in 1979. We are a nonprofit organization. We serve engineers, students, and professionals in STEM fields and communities. We are based in San Francisco Bay Area. We are fully utilizing the good location, the heart of Silicon Valley, to promote technological advancement, networking, and communicating among engineers and scientists. And overall, we want to promote the well-being of the science and engineering community. Okay. There are various activities throughout the year, and we have sub-chapters, subdivisions of groups that are technological groups and also young generation CIE groups. We mostly hold seminars, talks. We invite speakers from in the industry, from academia, and we host various events and activities. Okay, so today, Dr. William Kao is representing the Emerging Technology Group. Many of you may already attend the last event where he talked about the exploding technologies from Gartner curve. And also today, Electronic Design Technology Group is supporting this event. So we know that there are so many young professionals, young STEM generation in the community, and we have a lot of care and networking opportunities for people. So for example, I joined the CIE event in about 5 to 6 years ago, and I quickly enjoyed the networking opportunities, and I started volunteering for CIE because I want to give back to CIE and also help others. So since pandemic, we have moved all our events to online. We have held many events through Zoom and also YouTube streaming. And many of them are quite successful. And also they have recordings where we save on YouTube channel, and they're available for playback. So today's video will also be available for playback after we upload the video. So how to find our, another good place to find our past events and upcoming events is Eventbrite. So under CIE SF account, we post every event on Eventbrite. And you have already registered through Eventbrite, so you know how this works. And one thing to note is that because this Zoom link is controlled by Eventbrite, so the link or the Zoom button is only available 30 minutes before the event starts. So how to find our YouTube channel? If you just search CIE space SF, you will see our account. And we already have 172 subscribers. So please subscribe to our channel. And if you want to watch this video again, or if you want to watch other videos, you can find all videos there. And just want to talk a little bit about this in-person event that we held this year on May 14th. This is an annual conference which runs from the whole afternoon and also evening. So we want to let you know that we are bringing in-person events as well as hybrid events back to offline and online. So please stay tuned in our future events. These are the speakers that we invited for our annual conference. So today we have Dr. William Cao here. He received his degrees all the way up to PhD from the University of Illinois, Urbana-Champaign. He worked in the semiconductor and the electronic design automation industries for more than 30 years. He holds several senior and executive engineering management positions at Texas Instruments, Xerox Corporation, and also Cadence Design Systems. He has authored more than 40 technical papers on IC/CAD at IEEE journals and conferences, and he holds 8 software and IC design patents. He was an adjunct professor at UCLA Electrical Engineering Department. He taught courses in computer-aided IC design there. He's a senior member of IEEE, and he was one of the founding members of IEEE Circuits and Systems, Silicon Valley chapter. Dr. Cao currently teaches clean technology and emerging technology courses at the University of California, Santa Cruz, Silicon Valley Extension. So Dr. William Cao is known for giving talks, seminars, especially for CIE. And throughout the year, he has prepared many seminars in broad topics. And some of topics are emerging technologies, including clean tech, renewable energy, big data and data analytics, IoT, smart cities, sensor networks, innovation, VR and AR, robotics, AI and machine learning, 5G, 3D printing, satellite communications, and today we have photonics. So he is a technology watcher, learner, and teacher. So I will hand over to Dr. William Cao for his talk.
Thank you, Yanshu.
Yeah, no problem. The floor is yours now.
Can you hear me?
Yes, no problem.
Okay, I'll do the full screen projection. So, good evening, everyone who is on Zoom. Happy to be giving this webinar on the topic of photonics. Photonics is the science of the photon, and the photon is the most fundamental particle of light. So hopefully after tonight's webinar, you have a better understanding of how we're moving from 20th century electronics to 21st century photonics. So tonight's agenda for the talk, we'll start by giving a brief introduction about what is photonics, talk about some of the properties of photons and light, and give a brief history of photonics. Then we'll focus in the second segment on some of the key applications, including lasers, recently LiDAR. LiDAR is for self-driving cars, biophotonics, and the third section, we're going to be talking about more about the future, which is the integration of photonics and silicon, and wrap it up with a summary and conclusion. So let me try to, okay. So let me try to move my my Zoom stuff a little bit out of the way, because right now it's blocking my screen. Although you probably don't, the audience probably will not see it. Okay, so let's just keep going. Photonics, if you look at the word, is the left side is photo or photon, which is the smallest unit of light. Okay, so photon actually in Greek, it denotes light. Okay, so everybody knows that in the 21st century, we know the term electronics, which is the field that I was in for more than 30 years. And all the electronics is based on the electrons. Now, photonics, the basic unit is the photon. Okay, so photonics, the field of photonics, it covers the entire generation, the process, the manipulation of photons to achieve a certain function. So photonics means using now the photon to perform a lot of functions that used to be done by the electronics. Okay. On the bottom of the slide, it says the photonics includes the generation. Everything has to do with light. So it covers the generation, emission, transmission, modulation, processing, amplification, and sensing of light. Okay. So photonics is the science of the photon, and the photon is the most fundamental particle of light. So by getting understanding and control of photonics, basically allows us to manipulate light. And the technology covers actually several technologies, including optics, quantum electronics, lasers, detectors, fiber optics, and a lot of new materials. So photonics is in essence the engineering of photon, so photon engineering. And just like in the 20th century, all the technology was dominated by electronics. In this century, we are already in 2020, so we're already gone 1/5 of the 21st century, but the rest of it will be even more focused on photons. So if you look at various areas like communications, entertainment, also displays, because everything that we see, for instance, on your screen, on TV and so on, it requires display, it requires lighting. Lighting, bioengineering, manufacturing. Moving from 20th century to the 21st century, the 20th century was dominated by electrons and electronics, and the 21st century will be moving more toward photons and photonics. And why? Why are we moving? Before we get into the difference between electronics and photonics, let me also just mention some of the current applications of photonics. There are many of them already. For instance, lasers. For instance, a lot of them may have already gone through cataract surgery, for example. Okay, all of that, as well as, for instance, lenses and glasses, is all done by laser surgery. And lasers is part of the photonics. Okay. Also displays, things that we see on the screen or your watches, your cell phones, all the displays are also really performed by photonics. Since the 1960s, we have now the use of fiber optics. Fiber optics is another sub area of photonics. We have holography. We have also conversion of electrical, solar energy, for instance, to electrical energy. That's also part of the functions of photonics. Okay. And finally, in the area of environment, a lot of the things like telemetry and so on is also being assisted by photonic technology. So in the 21st century, there will be a lot of new applications of this technology in the area of imaging, entanglement. Entanglement has to do because one of the characteristics about photonics is very similar to quantum mechanics and quantum electronics, another subject that I've talked in the past. And it has some properties like particle wave duality. Okay, so we'll be covering that also in the characteristic portion of the photonics. And right now, the other thing that is going to be for the rest of this century, an area that's going to be very important is always the subject of new materials, whether we're talking about nanomaterials or new materials for various applications. So why is the switch from electronics to photonics? If you compare an electron with a photon, and you compare electricity versus light, okay, there are a few distinctive characteristics. For example, light travels much faster than electrons. So for instance, when you flip your switch at home, the light is instantaneous, okay? So the fact that the light travels much faster than sound and electrons means that future computers will also be much faster if you make use of photonics. The other thing is that photonics can also pack more wavelengths. So the amount of information that can be transmitted by using photonics is going to be also a lot more than the current electronics and copper wires. The volume of data that can be transmitted will be also much larger. Okay, and the third point is that whenever we're dealing with electronics, there's a lot of interference and distortion. So light encounters no EM interference. So these are three areas where photonics have the edge over electronics. It's faster, it's larger in terms of amount of data, and the third is less distortion. Okay, so let's go into a little bit about the background. the background of photons. So how are photons created? Okay, this is a picture where everybody is familiar with atomic energy. So you have an atom, a nucleus, and an atom is made up in the middle of a nucleus, and outside you have electrons. So the electrons can be in two states. One is in the ground state, which is basically more dormant, and also in an excited state. When the electrons move from the excited state to a more ground state, part of the process, it will emit some energy. And that energy is actually what we call the photons. So the next slide will describe this a little bit more. So a photon is produced whenever an electron in a higher orbit falls back into its normal orbit. So let's say that here you have, in the middle, you have the nucleus and the atom, and then you have an electron on the outside. Okay. So when electrons get excited, they move to a higher shell. But after they return back, they, as part of the process of coming down from the higher excited state to a normal state, the energy is emitted. So here you see some sort of like wiggly thing. That's actually the symbol of the photon. It's actually sort of like a wavy thing, because as I mentioned, the photon is both a wave as well as a particle. So this is the only slide that has a formula. So for people who are not engineers, you don't need to worry about it. This is the only one that has a formula. So the energy from light, okay, is described by this formula, which is hc over lambda. H is a constant, okay, called Planck's constant. C is the speed of light, and lambda is the wavelength. So the reason why we're talking about the wavelength is that when we're dealing with light, we're dealing with a spectrum. For example, what we see normally in our daily life is called the visible range of light. And then most of you probably have heard about infrared and ultraviolet, okay? So a photon, again, is a piece of energy. It has no mass, and besides behaving like a wave, it can also behave like a particle. And when it does that, when it behaves like a particle, it is called the photon. So the particle portion of the characteristic is actually called photons. Okay. So as I said before, people in the past, whenever we see light, we thought that light as a wave. Okay. So, and then we are familiar with some of the characteristics, like whenever you have light, you have reflection, you have refraction. Okay, really what happens to the wave light, right? So it can be reflected or it can pass through and so on. So Einstein discovered, however, that there are some cases where the light behaves not like a wave, but as a particle. Okay. And these particles are the ones that call photons. So light has a dual property, which is the wave particle duality. It is both a wave as well as a particle. So again, I mentioned in the 20th century, and Einstein discovered, as you all know, Einstein was also involved in quantum mechanics. And this is where he noted some of these properties of light. So when light hits a solid, it actually acts like many particles bouncing off a solid. And this is what he discovered, that actually it has a characteristic of a particle. So if you look at light, what can light be used for? Okay. So of course, everybody is familiar with looking at watch or cell phone displays. Also, we have the normal lighting at home. Okay. We also mentioned about fiber optics, the use of fiber optics instead of wiring, which is much faster and also larger data volume. Also sensing of light and so on. So these are some of the applications. So photo, the word photo in Greek, it means light. Okay. So so the term photonics actually it started becoming to the public view in the 1960s with the laser. Okay, the laser came out around 1960s, and then later on in the 1970s there are optical fibers, and now of course right now with communications, telecommunications, we're more and more familiar with fiber optics. Okay. So we mentioned that photonics actually covers many different technologies. Everybody in the lighting domain, everybody heard about light emitting diodes. For instance, right now, a lot of public lighting on the streets, as well as the stoplights, the red, yellow, and green light, they are now being made from LEDs. Okay. Also, lasers. We'll talk about the use of lasers. Use of lasers in surgery, eye surgery, for example, as well as you can cut metals using lasers. Sensing, okay, you can detect things via light, okay, and there are many applications, including in the biomedical field. Now, in the last 10 years, everybody have heard about solar cells. So one of the domains is PV, okay, photovoltaics. That means that you can take the sunlight and convert it into electricity. So that's solar energy. The other one is that because the photons has the property of wave and particle, and that we mentioned that the speed of photons is much faster than electrons. So photonics is also being used into computing, okay, making computation much faster. And everybody, I was involved in the semiconductors for more than 30 years. And people are still talking about when is the end of Moore's law, okay? So we will see in the future an integration of silicon and photonics. And that's the last segment that I'll be covering today, is that how does the photonics get integrated into silicon? So I mentioned that in the area of light, okay, what we see daily is called the, where we see in the daily activities, that's the visible domain, okay? So, but photonics, it extends the domain of the visible light, okay? So here is the visible portion, the wavelength. Remember the formula, HC over lambda? Lambda is the wavelength. And different sections of the spectrum, they have different wavelengths, okay? The ones that we see in the normal world is the visible. And then you have the infrared, and you have the ultraviolet, and then you have X-ray, microwave, radio frequency, and gamma ray. So here's a picture that is probably a little bit clear. So visible light is just this thing, very narrow frequency, okay, from 700 nanometers to 400 nanometers. And then the different other domains like X-ray, microwave, radio waves, and gamma rays, they all have different wavelengths. Okay. So, but everything is really encompassed within photonics, which covers the whole thing about light. So what can the photons do? So we mentioned that already in some of the past slides about sensing and so on. So let me quickly just review. There are basically 7 major functions that we can make use of photons and photonics. Okay, we can sense light. Okay, sensing, storing it, transporting. This is like the optics, fiber optics. Actually, do something with it. Energy, it's like solar energy. You can use it in displays for screens, and you can also do faster computation. So these are 7 of the functions that photons are good for. So let's just dive in a little bit more. So sensing, photo detectors. As a matter of fact, a lot of your cell phones have the function already built into using photonics. Okay, so photo detectors, your cell phone, which has a camera, all right, okay, that also is actually being already using photonics. Also, we mentioned that computation is much faster using photonics. Displays, whereas computer displays, cell phone displays, your watch displays, your PCs, okay, and also the energy conversion from light to electricity. So from solar light uh, and solar thermal into electrical. Actuate, that is where the lasers come in. For example, you can use lasers to cut metal. You can also use laser to perform eye surgery. Okay, so laser is a very high, narrow, powerful beam that you can use to cut. Okay, transport means the transfer of information, like in telecommunications using optical fibers. And then right now also can be used for storing. Okay, so a lot of the CDs and DVDs, they all can be stored and read by photons. Okay, I'm going to skip this slide, but because I think it's already been covered. We mentioned that some of the application is in the biomedical field, okay? And also in the future, we'll be seeing more integration of photonics and electronics in the form of using the IC as a platform. So the next section, we're going to cover some of the applications of photonics. So we mentioned already that some of them, like lasers, we have mentioned also about biomedical, sensing and surgery, diagnostics, and also into computer display technology and optical. So we'll go over into some of these specifics. So here are some of the domains where photonics are being used on. In consumer equipment and consumer electronics, telecommunications, this is mainly in the area of optical fibers, military, okay, entertainment. So a lot of laser shows, LED shows, for example, they are everything that you can see, a lot of light shows, for example, they're all using photonics. We already mentioned about use of photonics into medicine and surgery, spectroscopy, and also computing. So this is sort of like same content as the last one, but basically in what domains. Like for instance, right now, the the photonic computing, they are basically used into a lot of the cloud data centers. sensors and biosensors. They are being used in IoT into sensors for smart cities. Okay, we're also trying to use photonics for the latest in the faster high-end computing, like quantum computing, aerospace, and high-end. Okay, so a lot of the satellite technology, for example, is also going to be using light. So we are seeing that all these are the current technologies that are in fashion right now. Right now, satellite and aerospace, the space technology, you'll be using a lot of photonics. Okay. So this is sort of like some of this, you have to excuse me that there's some repetition. A lot of the slides, maybe some of the slides may be repeated, but I guess once you go through a couple of times, it will sink in. Okay, so if you see some of the contents already previously discussed, maybe the wording is a little bit different, you know, like telecommunications, renewable energy is a solar PV, right? Medicine, a lot of industrial manufacturing. So again, cutting metals and so on, as well as the very sensitive things like skin and eye. So the laser is a tremendous tool. Yeah, somehow I think that I'm using a previous version of it, so I'm a little bit out of sync, but to you guys should be the fine. Because this is the first time you see the slides. So in a summary, the application of photonics are ubiquitous. That means that they are everywhere, okay? You can see it from how you make use of light. Some of this will be covering in the next few slides, like for example, holography, uh, LiDAR, lasers, we'll cover some of the applications in more detail in the next few slides. Okay. So the applications of photonics are virtually unlimited. And they are also being used, for instance, in terms of defense. So we mentioned one of the areas is military, as well as the satellite communications. So laser, because of the fact that it's a very high intensity beam, you can transmit information as well as you can destroy incoming missiles using laser technology. So applications in aviation, military, entertainment. So if you go to Times Square, for example, you're going to see a lot of light shows in Times Square. Most of them, they are using lasers as well as LED, okay? Now, one of the most recent applications of photonics is in the self-driving cars. So instead of using radar, they're using LiDAR, okay? LiDAR because it comes from light, okay? The other thing is in terms of metrology. Metrology is the science of doing the measurements. So you can calculate some of the speed where light travels, and you can apply it to metrology. We already mentioned about photonic computing. The photons are much faster than electrons. And then we also talk about integration of photonics and electronics into silicon. Okay, so I'm going to jump over this slide. Actually, in my latest version, somehow I'm not using, I'm using the -1 version. So somehow all of this has already been corrected, but I'm not going to switch the PowerPoint midway. So we just continue with this previous version. All right. So let's go over some of the interesting applications of photonics. One of them is holography. Okay. So a lot of you probably have seen some of the Star Trek movies, like the Yoda and so on, right? So holography is also, it comes from a Greek word. Graphy means writing, and holo means a hole. So you can produce three-dimensional pictures or photo. So in this case, you're seeing, for instance, something like a dinosaur, or you can see Captain Kirk, also in hologram form. So you probably have seen some of this in some of the Star Trek movies, where you can see a hologram of Captain Kirk, right? So this is all using light and projecting images, image display. Now, this is an area where a lot of you probably are familiar. If most of you are over 50, you probably go over some to have some checkup. And they say, well, you need to go and do a colonoscopy. So for instance, colonoscopy is something that you really, most of you probably have been exposed to. And colonoscopy is nothing more, it's a form of endoscopy, which is the surgeons, insert some instruments through the mouth and so on, and then perform some surgery. Okay, so all of this actually where you actually insert a light and a camera, and you can see the inside of your body, and they can perform surgery and so on. So that's also one of the very important applications of photonics in the medical domain. Okay, laser. So the one that I do remember the most about lasers is that if you remember watching 007, I think it's in the movie Goldfinger or something like that. Remember that there was a light beam that was cutting through metal? Okay, so that was laser cutting through metal. So a laser stands for light amplification of the stimulated emission of radiation. And it is a very intense beam. So you can project it over very long distances, including to space. And also you can use to drill and cut, okay? From very sensitive objects like eye surgery into hard objects like metal. Okay, another subject that is very recent, because right now there are a lot of companies working on self-driving cars. And one of the things that is needed in a self-driving car is that you need to go and monitor your surroundings. So one of the tools that is still being worked on, because right now the technology is still quite expensive, is that they're using what they call the LiDAR. LiDAR stands for light detection and ranging. Okay, so you can basically send out beams of light, okay, and then when the light hits the object, it reflects back, and from the reflection, you can time the distance or the time that it takes for the light to come back, and from there you can deduce the distance of the object from the car. Okay, so that's the way that the LiDAR works. So here is more into pictorial form. So you have a light source and you shoot the beam of light. The beam of light hits an object and it comes back to the receiver. And the time that it takes to shoot out and return, from there you can measure the distance. The distance is measured by this formula and the time it takes. Okay, c is the speed of light, t is the time that it takes for the beam to go and can return. Okay, one other application of photonics is in the biomedical field. So biophotonics is basically the intersection of medical science and photonics. So that's what is called biophotonics, is here in the middle. Biophotonics is the science of generating and harnessing the light to detect and manipulate. Basically it's the application of photonics into a biological and medical field. So that's what biophotonics is. So there are several branches of biophotonics, including like biometrics. People are most recently, everybody heard about biometrics, from facial recognition to gait recognition and so on. Is how you recognize people. That's biometrics. Imaging, okay. You can look at different colors and detect, where's light detection of objects. Detection, surgery, I already mentioned about eye surgery. Detection, for instance, you can also detect where you have cancer cells, for example. Okay. Okay, so the last topic is that right now people say, well, when is the end of Moore's law? How long we're going to have electronics still in our world? Well, electronics are not going away, but with any new technology, there's more and more integration of various kinds of technologies. So silicon is still going to be around, but silicon is also going to be used as a platform to integrate some of the photonics capabilities. So on a chip, you can have some portion of it that have photonics built into them, okay? So photonics or silicon photonics is basically the use of silicon as a medium to empower photonics, okay? So silicon is the medium or the platform, and on top of the silicon, you can build in photonic capabilities, and they are all integrated on a chip, okay? So it's the merging of photonics and CMOS, okay? So everybody is familiar. I mean, we've been living with silicon for the past, 50 years at least. So, and they're going to be with us, probably still for the next 20, 30 years. So it's not like photonics are going to be replacing silicon. But the thing is to combine both and have electronics and photonics capabilities integrated on a same substrate, okay? So that's what silicon photonics will bring us. So this is sort of like a projection about the various areas where photonics are going to be used in the next 5 years. So it's from 2020 to 2026. Don't worry too much about on this slide about the dollar amounts, but basically we're talking about the use of photonics in data centers. That means like the cloud computing, right? 5G, that's another topic that is going to be with us for the next 10 years from 2020 to 2030. Photonic computing and using that to also assist quantum computing, okay? LiDAR, we mentioned about self-driving cars and so on, okay? And use of photonics in both in terms of our outside environment as well as our own internal health. So let's go and sort of summarize what we've covered today. We are basically right now moving from the age of electronics into the age of light. Okay, so what we've covered in tonight's talk is the what, why, where, and how of photonics. What is photonics? Why do we need photonics? What does it bring us? Where can you, where are some of the applications of photonics? And then how does photonics works? Okay. So we've given some of the principal applications of photonics, such as in lasers, LiDAR, biophotonics, and we're looking forward toward the integration of silicon and photonics. Okay. So some of the takeaway messages. In the next 10 years or so, well, it actually is for the rest of the 21st century, but we're going to be seeing more and more applications of photonics into some of the other hot technologies like 5G, the Internet of Things, artificial intelligence, big data and data analytics, and so on. And we're going to be seeing more solutions, integrated solutions between silicon and photonics, okay? And we're going to be merging those into a single platform, which is chips, because things are getting smaller and smaller. Okay. So tonight we've basically introduced, actually, as I said, photonics has been around in various forms already with us for several decades. But I think the reason why the talk for tonight is that moving into the rest of the 21st century, the role of photonics are going to be much more stressed. Okay, so we're going to see more and more the importance of using photonics and light, and hopefully that will also complement or supplement the electronics. So I think that's the talk for tonight. We'll try to open up some of the questions for Q&A. And I also have a couple slides that, okay, here, let me, before we open up for the Q&A, let me just present one more, there's one more activity that CIE, the Chinese Institute of Engineers, is working or collaborating with UC Santa Cruz. And we're offering a series of short courses. I'll be, possibly teaching, depending on the amount of people who sign up. I have a short course meaning actually it's about 6 hours. Okay. So, and that one is on a topic that I've given also a talk about, the metaverse. Why the metaverse? Is because if you actually look at some of the most recent advertisements on the TV from AT&T and so on, is that, and Facebook, is that the metaverse may be virtual in many areas, will be in the virtual space. However, the impact that the metaverse will have will be in the real world. So the metaverse is something that you cannot ignore. Just like, for instance, not many people like politics and so on, but it still affects every one of us. So I'll be offering a course on the metaverse. This is November 12th and November 19th. So because the course has been defined for 6 hours, so I don't think I can talk for 6 hours straight. So I'm just breaking it up into 2 weekends, 9 to 12. And also that also enable a lot of you to do your normal weekend chores, because I don't think you can afford to lose the whole Saturday. So my short course will be spread out over 2 weekends, November 12th and November 19th, from 9 to 12. So 3 hours each. The course will be offered at the UCSC extension, near Bowers and 101. This is a paid course. It's $60 for 6 hours of instruction. You will also be given a certificate from UCSC. So this is sort of like a short course certificate. Okay. So yeah, actually I had another slide, but I'll bring it up if there's no question. I can talk about the more details. If some of you are interested, I'll have another slide to talk about the contents of the course, but I'll just leave this one for now and then entertain any questions that you may have on photonics.
Thank you, William. Thank you.
You're welcome. So we'll open up for any questions that people may have.
Yes. One question from the audience is, can you explain how photonics helps sending and receiving emails? How does it make possible?
Yeah, there was a talk that I gave about less than 1 month ago on the satellite communications, satellite internet. So right now, for example, more and more things are moving into outer space, because right now there's a lot of things that, for example, especially recently, there's so much turmoil in terms of the weather, right? Extreme weather. So every time you have extreme weather, if you have a land-based communications, they're all being shut down. If you have flooding, you have fire, or you have things like that, or hurricanes, then a lot of the land-based communications are shut down. So I think that right now, one of the ways to overcome that is to use more and more satellite communications. And that's where you can actually make use of photonics and the lasers to transmit the information up to the satellite, and then not getting any interference from the ground, okay? And then go into the receiver side. So that's the part where we see that one of the things that will be used very often. So satellite internet is actually played a major role already in the Ukraine-Russia war, with Starlink, right? So that would be used for any area where it's not accessible, either because, if you're in the middle of the ocean or you are on top of the Himalayas and you want to receive a signal, well, you have to rely on satellite internet.
Okay, thank you. There's a follow-up question. Fiber optics cable makes transmission of email possible. How true?
Actually, I've not followed too much on the using fiber optics for email, but I guess one of the things is that in the past, communication was done via just cables that run through the bottom of the ocean, going to transmit all the information, whether it's email or anything, from, say, Americas to the Far East. Okay, but as I said, the advantage of fiber optics is that it's faster and it can handle much larger amount of data than the copper wires that currently are laid on the bottom of the ocean. So, but if you have, if the audience has a little bit more specific question that wants to either talk about or share with us himself, welcome to.
Okay, while I'm waiting for more questions, I'm just showing our AI short course series. So Dr. William Call will be offering 1 out of the 4 short courses. And we have other topics such as IoT, biomedical engineering. So we have this short course series. Like Dr. William Call said, it will be held in person in UCSC, Silicon Valley Extension. So you can find more information and how to register, what are the benefits, what are the prerequisites, and how these courses will open the door for you into AI on Eventbrite. Okay.
Now, for the people who are still on Zoom, one other thing that I would like also to poll, through this webinar is that if you have any topic that that you have some interest that you would like to hear, I don't promise to do it this year, but maybe next year. If you are interested in a certain topic that you would like to learn more, please either tell us now or send us an email, and I try to accommodate for next year.
Thank you. Since we have a little bit time, I want to also introduce our upcoming events on next week. So next week, December 26th at noon, 12 p.m. Pacific time, we are holding a talk seminar on crypto meets real estate. So just briefly, it will be a Zoom-only event. And we can learn a little bit about market trend on how cryptocurrencies play a bigger and bigger role in the real estate market. Are there any other questions? If you want to speak to Dr. William Call directly, you may raise your hand and I can give you permission to speak.
Okay, so if we don't have any more questions, I think we'll wrap up tonight's webinar. We want to thank everyone for attending tonight's webinar. Any feedback do you have for us, you're welcome to submit it. Any areas that we can improve, let us know. And, we'll see where there are more webinars this year, but otherwise, we'll sign off.
Thank you everyone for joining tonight's seminar. We look forward to seeing you in future events. Please subscribe to one of our or more of our media channels to learn about our events and how CIE can help you. If you have any questions or suggestions, please contact us. And thank you. Have a good night.
Thank you, Yansu. You can.
Thank you, William.
We'll meet the next time. Okay.
Okay, bye-bye, everyone.
Bye-bye, everyone.